Um, so, okay, I think I'm back. So it is time to talk about a brand new topic, which is called capacitors. Okay, and a capacitor is basically it is two metal plates. So you have two metal plates that are really close to each other, but they're not touching each other. Okay. So that's kind of a 3D view of a capacitor. And if you wanted to look at a side view of a capacitor, it just looks like this. So it just looks like that. Okay? And capacitors, they have charge on each of these plates. Okay? So maybe you have positive charge on this plate. So there's a positive plate. And then there's also a negative plate, which has an equal but opposite amount of charge. Okay? All right? So there's an equal and opposite amount of charge on the opposite plate. Q is equal to the charge on the positive capacitor plate. Now, these two capacitor plates, obviously they have opposite charges, so they want to attract each other like that. So there's something mechanically, some sort of an insulator that is mechanically separating these two capacitor plates. And the thing that is separating the capacitor plates is called a dielectric. Okay, and it's just an insulating material that is in between the capacitor plates and prevents them from coming together. Okay, and it's an insulator, so the charge can't just leave the metal and then go to the other side and sort of equilibrate itself. Okay, so that's what a capacitor is. Now, what would happen if you took so what would happen if you were to take the two plates of the capacitor and connect them with a wire? Okay. Well, what would happen in that case is all of these, remember, it's the negative charge that is mobile. Okay, the electrons are the charges that are actually moving around. So all of the negative charge would go around and equalize. Okay, so then you would have no net charge and no net charge. All right. So, anyways, oh, and I didn't give you the circuit symbol for a capacitor, which is just exactly what it looks like. Okay, so if we have a big battery, it's going to push more charge onto the positive capacitor plate. All right. And so there's a fundamental equation for capacitors, and it's Q equals CV. This is the fundamental equation right here, where V is the voltage across the capacitor. Which is sometimes called a cap. Q is the charge on the positive plate, and C is called the capacitance. And the capacitance, it depends on geometry. So in particular, it depends on the size of these capacitor plates. It depends on the distance between the capacitor plates. It depends on what you shove between the capacitor plates. Okay? So it depends. The other thing I wanted to give you is the units of capacitance. The units of capacitance are called farads, which is abbreviated by F. Most capacitors are in the range of nanofarads. So a nanofarad is 10 to the minus 9 farads, or microfarads, which is 10 to the minus 6 farads. If you had a 1 farad capacitor, C would be 1, and you would have, if you hooked up a 1 volt battery to a 1 farad capacitor, you would have 1 coulomb of charge on that plate. And if you had 1 coulomb of charge on these plates, there would be such a huge attraction between the plates that it would. So I got an excellent question here, which is, if the battery gives a lot of charge to the positive capacitor plate, does that mean that the negative capacitor plate will gain more charge to balance it out? And the answer is yes. So what happens is that the battery essentially steals electrons from the top capacitor plate and shoves them on to the negative capacitor plate. So if the positive plate gains 1 coulomb of charge, then has a charge of +1, then the negative plate is going to have -1. So they have equal and opposite charges. What I was saying is there would be a huge force, because there's a force of attraction between these capacitor plates. And if you had 1 coulomb of charge between these, 1 coulomb of charge and -1 coulomb of charge, that would be a huge electrical force that would cause the capacitor plates to just immediately snap together. So there's sort of a limit to how much charge you can put for that reason. Okay, so that's an important equation. We could take the derivative of this equation, and if we took the derivative of this equation, we would get dq dt equals c dv dt. And of course, so c is a constant. It just depends on geometry, which isn't changing. dq dt is the derivative of the charge, which is the current. So we have I equals c dv dt. So this is another expression for the main capacitor equation. So I'm going to give you a formula for the capacitance, okay? So here's that picture of the 3D capacitor of the capacitor plates in 3D, like that. The capacitor plates have a certain area. So A is the area of one of the capacitor plates, okay, which is assumed to be the same as the area of the other capacitor plates. So they both have the same area. So it's just length times width, or I don't know, pi r squared if it's a circular capacitor. And D is the distance between the capacitor plates. And so the capacitance is epsilon A over D. So this is our second main formula for today. I just explained what A and D are. Epsilon is the permittivity of the dielectric. Okay. So there is literally just, if it's not free space between the capacitor plates, then epsilon is not going to be equal to epsilon naught. There is one way of expressing the permittivity is to write epsilon as equal to epsilon r times epsilon naught, where epsilon sub r is called the relative permittivity. So for example, if the relative permittivity was 2, then that means that epsilon is twice the permittivity of free space. So you can look up the relative permittivities online. So you basically look this up online, what it is for a given material. Okay? And so based on this, we can calculate what the capacitance will be. Okay? And this is for the most simple type of capacitor only, which is called a parallel plate capacitor. Okay. Now let's go back to a capacitor in side view. So you've got the positive capacitor plate, and you've got the negative capacitor plate. What does the electric field look like between the capacitor plates? Well, you might remember that electric fields have to be perpendicular to the conductor, and they go from positive to negative. So they're going to look like this. This is what the electric field lines look like for a capacitor. They go from the positive plate to the negative plate, and on the edge of the capacitor, the field lines kind of bow out like this. Good question. Is the positive plate always on top? The answer is no. If you were to flip the battery upside down, then the negative plate would be on top. So these electric field lines that are on the side of the capacitor that are bendy, this phenomenon is called the edge effect. And the edge effect is not really important if you're taking the AP exam, but if you're taking the IB exam, then it is important, because the IB exam, for some reason, wants you to know about the edge effect. So I told you about the edge effect. You got it? we could actually approximate the size of the electric field between the capacitor plates. Because you might remember that the electric field is minus the derivative of the potential with respect to distance. So we could write it as minus, so this is approximately equal to minus V over D, where V is the potential difference between the plates and D is the distance between the plates. So you can use this equation to estimate the electric field between the capacitor plates. All right? So there you have it. That's an introduction to capacitors. Stephen asked a really good question, which is, does the field, D was the distance between the plates, yes? Stephen asked a really good question, which was, does the field go to infinity if the distance is 0? And the answer is yes, it would. But there's an important thing here. If the distance between the capacitor plates is super duper small, then the electric field is going to be so huge between the capacitor plates that it's actually going to ionize the material between the capacitor plates. And when you ionize the material, it becomes conductive. So, for example, you could think about a lightning strike. You can think about a thundercloud as like a capacitor plate. So a thundercloud is when is the top capacitor plate, and the Earth is the bottom capacitor plate. And when the distance between them is too small, the air between them has what's called a dielectric breakdown, and it becomes the air between them has what's called a dielectric breakdown, and it becomes conductive, and then lightning can go from one to the other. So in response to your question, if the distance gets small, you have what's called dielectric breakdown, where the dielectric becomes a conductor and just allows the charge to equilibrate. So really quickly, what does a capacitor do in a circuit? It basically stores charge. Like I said, you can store charge indefinitely on a capacitor, and then when you want the charge, you can connect the two capacitor plates and you get a burst of current as the charge rushes around to equilibrate. Okay, so it's used, one of the applications of a capacitor is to store charge and then use that to create a burst of current. Okay, so when used in this way, a capacitor can actually make short bursts of current that are more than what a battery could make. So if you need a really big burst of current, use a capacitor. All right, so that's all for my lesson today. I will see you tomorrow. Bye.